Hello everyone, welcome to this talk of first efficient convergence for streaming kPCA, a global, gap-free, and near optimal rate. This is a joint work with Yuanzhi Li from Princeton University. So in this talk, I'm going to focus on a very fundamental problem, kPCA, that is to find the top k eigenvectors and eigenvalues of the following data covariance matrix. Namely, we are given some data vectors xi. Each vector x is of dimension d, and we have n such vectors. Now the data covariance matrix is 1 over n times the summation of xx transpose. And we call this d by d matrix M. And now the task of finding the top k eigenvectors of M is the same as finding the top k principal components of the data matrix X. So for the task of PCA, we typically study that under one of the following two models. The first model is the offline model, meaning that the algorithm to solve it can have a time complexity that depends on n, the number of data vectors. So in this offline model, existing techniques include like stochastic offline methods such as like SVRG and shift and invert methods. The state-of-the-art algorithms include, say, the Bloch-Lanczos method by Muskal and Muskal and our lazy SVD method last year. So if you're interested in this regime, meaning that in your task maybe n is more, then I'm afraid you're at the wrong talk, because this talk is only going to be about the online setting, also known as the streaming setting. That is, the complexity of the algorithm cannot depend on n. In other words, you can view n as being very huge or even infinite. So why do I care about the online setting? 2 words, big data. If you want 2 more words, then that is deep learning. For those of you who have been to my talk like 10 days ago at the Simons Institute, I mentioned a strong connection between the task of PCA and training any neural network. In other words, if you can solve PCA faster, you can also train a neural network faster. So that's a different talk. So in this talk, I'm only going to talk about the online model of PCA and how to solve kPCA fast without any time complexity dependence on n. So this task, I claim, is much more challenging than the offline case, because most of those offline techniques just fail to work, including SVRG and shift and invert, and therefore we have to develop our own techniques. This talk is in particular going to be divided into 3 parts. I'm going to talk about algorithms, results, and analysis. Okay, let me begin with algorithms. So everyone knows power method, and let me now introduce you a variant of it called block power method. In a block power method, you first randomly initialize yourself with k random vectors, represented by this matrix that is d by k dimensional. Now in each iteration, you first left multiply your matrix Q by M, which is the matrix you want to compute the largest eigenvectors of. And then you do a Gram-Schmidt orthogonalization. So a Gram-Schmidt orthogonalization is to first normalize the first column, then you orthogonalize the second column with respect to the first one, and then you orthogonalize the third column with respect to the first 2, and so on and so forth. So that is the Gram-Schmidt orthogonalization. If you run this algorithm sufficiently long, say after big T number of iterations, you get k vectors. Now I claim that the theory of power method implies that these output k vectors are going to line in some sense very well with the top k eigenvectors of M. That is the target that we want to achieve. So I haven't defined what I mean by align very well, which I'm going to define it on the next slide. So at this point, I want to make a remark. Actually 2 remarks. First of all, if k equals to 1, this method exactly goes back to power method. Second remark, that is, in fact, this Gram-Schmidt orthogonalization is something that I, at least in theory, for analysis purpose, I don't need to do it every iteration. I can push it all the way towards the end and only do it at the very end. You know, if like instead of normalizing now, you can normalize in the end, it's going to give you the same vector. So therefore, like these 2 lines really characterize the main idea of the block power method, but unfortunately it's an offline method because in this setting, we don't have full access to the matrix M, and therefore like how can we turn this into an online method? So this very nice idea of Erkki Oja, back to 35 years ago, he published a paper in a biology journal, and the paper gave rise to the following algorithm that replaces the power method. That is, in each iteration, instead of multiplying it by a matrix M, we try to multiply it by something stochastic, that is identity plus a learning rate eta, that's a small positive value, times XX transpose. So in each iteration, little t, then we generate a different vector x from the matrix, and then we multiply everything together. In the end, do a Gram-Schmidt. This gives us k vectors qt. So this is known as Oja's algorithm, but unfortunately, in this original paper, Erkki Oja, he did not really give any good analysis. Therefore, from a very high level, the contribution of our work is to first show that Oja's algorithm really works, and two, we provide a slight modification on Oja's that we call Oja++ that works even better than Oja's algorithm. So that is the high-level description about our contribution. But wait a minute, so far I haven't defined what do I mean by saying it works. Okay, historically people say that we solve KPCA. Whenever they say that, they mean one of the following three things. Goal number one, that is to exactly recover the top k eigenvectors. Namely, remember Oja's algorithm, for instance, outputs k vectors, and if you do a transpose, then it means k row vectors. And now if you also write down the bottom d minus k eigenvectors of the matrix, in say column vectors, which correspond to the eigenvalues that are not in the top k, then we hope that the output vectors correlate with those bad eigenvectors by something small. In particular, if you compute this matrix product, you get a pairwise correlation value for between any vector here, row vector here, and any column vector there, and therefore we want, for instance, the Frobenius norm of this matrix to be small. So this is goal number one. In other words, up to this epsilon accuracy, we want Qt to recover the top k eigenvectors of the original matrix M. Unfortunately, to exactly recover the top k eigenspace may sound too ambitious, and indeed, whenever we're talking about goal number one, we really need some additional assumption. That is, there is an eigengap between the kth and the k plus first eigenvalues. If there's no eigengap, then the task of reconstructing the top k eigenspace becomes meaningless. Okay, so this is what people know as the gap-dependent goal for KPCA. People also talk about other goals. In particular, they also study this gap-free goal of KPCA, namely instead of requiring the inner product with all the eigenvectors in Z being small, but let's now require the inner product with respect to all the vectors in W to be small. So W is a submatrix of Z, which consists of only those eigenvectors with values less than or equal to the following threshold. In other words, here we do not need any assumption on the eigengap, but we are only requiring something weaker. That is, we only want a correlation with respect to those eigenvectors that are really bad to be small. So this is known as the gap-free version of the goal of KSVD. So people also study a third type of goal, which is the really quotient goal. That's also a gap-free version that says let Q1 through Qk be the output columns of this matrix. Then maybe we can hope that the really quotient Qi transpose MQi is larger than or equal to lambda I, which is the ith largest eigenvalue minus some additive error rho. So maybe we can demand this. So this is known as the Rayleigh quotient goal of KPCA. So a few remarks. First, the gap-dependent results may not necessarily be useful in practice, because in practice, we may not really have an eigengap between the kth and k plus first eigenvalues. And also, a second remark, gap-free results are strictly better than gap-dependent ones, because, for instance, if you get an algorithm achieving goal number 2, then I claim that the same algorithm also achieves goal number 1, because you can always define your rho to be the eigengap, and now this matrix Z becomes exactly the same as W, and therefore, if you have an algorithm achieving goal number 2, it also implies that for goal number 1. So these are the types of guarantees that people really demand for KSVD to, KPCA to satisfy. Let us now see the prior works. I'm going to talk about prior works in 2 regimes. That is, those works that only work for k equals to 1, namely 1 PCA, and those works that also support k to be larger than 1. On this slide, to simplify notations, I'm going to assume that the norm of the vectors generated from this distribution to be at most 1. Okay? On this upper left corner, there is this very beautiful work of Jane, Jean, Kakady, Netrapalli, and Sidford, in which they showed that OES algorithm achieves this complexity, like in this number of iterations, OES algorithm achieves goal number 1. So you see, like, it has a positive dependence on the largest eigenvalue, and the inversely, like, quadratically depends on the eigengap, and also has a 1/epsilon dependency here. So this result is also known to be tight. They also showed information theoretically a lower bound that this is the best one can hope for. That's a nice result. And in an independent work by Ohad Shamir, he showed also last year that the same OES algorithm also converges in terms of goal number 2 and 3. But unfortunately, in the complexity that he obtained, ignoring other factors, there is this dependency on D, on the dimension of the matrix. But in contrast, like, the dimension term does not show up in the result of Jane et al. Therefore, he raised essentially as an open question about how to remove this dependency on D. That's about k equals to 1. In the case of k larger than 1, this very nice work of Hart and Price, they showed that noisy power method uses this number of samples from the distribution and achieves goal number 1. So this is also a bit inefficient because of the linear dependency on the dimension, and also their results have this cubic dependency on the eigengap, but in contrast, like, Jane et al. Only has like a square dependency on eigengap, and therefore this complexity does not look very tight. There are also some follow-up results by at least 3 groups of authors. They tried to improve this result of Hart and Price in different parameter regimes. You can find the specific results of theirs in our paper, but from a very high level, these results also have at least a D dependency on the dimension, and at least 2 out of the 3 results, they also have a cubic dependency on gap. So that's not very tight, and to the best of our knowledge, there's no prior work that achieves goal number 2 and goal number 3 for the case of k larger than 1. So what we have achieved in this paper are the following 3 results. That is, we have now outperformed all the state-of-the-arts except the one, but for this, like, one that we have not outperformed, at least we have matched it. So our complexity here, if you choose k to be 1, then it matches the result of Jane et al. Okay, so that is what we have achieved. A few remarks here. First, we also showed a lower bound. That means, like, at least for goal number 1, our result is tight up to log factors. This is an information theoretic lower bound. And the second remark, all of the algorithms on this in this table either are exactly OES algorithm or maybe some variant of OES algorithm. So that means they only demand a space usage of order KD. So that's good, because the goal of PCA is to output k vectors, and therefore, the algorithm has to use space order KD because we need to output k vectors. But what's really good about all these algorithms is that even like throughout the algorithm, in every single iteration, we only need space order KD. So that makes all of these algorithms, all of these results, like streaming algorithms. But if you're willing to slightly increase the storage to this much, then actually you can do a little bit better for goal number 2. So this is kind of a subtle issue. You can see our discussions in the paper. And even if you allow the space to be this much, there is still no prior work. but we can do something better, and this is also known to be tight information theoretically. So the third remark I want to make here is that we achieved goal number 3 using OYA's algorithm, but the way that we achieved goal number 1 and 2 are actually upon this variant of OYA's algorithm that we call OYA++. So one can also do OYAs, but we found hard instances. So we also proved convergence results for OYA's algorithm. That's why our paper has like 5 theorems. But actually, OYA's algorithm, we find hard instances that says that it doesn't really run very fast. So there's a way to use this OYA++ to even outperform OYAs, both in terms of goal number 1 and the goal number 2. So this summarizes our results. And in the remainder of the talk, I want to do 2 things. First, I'm going to show you what is this business of OYA++. And 2, I'm going to give you a little bit taste of the mathematical meat of this paper. So first of all, what is OYA++? Remember, this is the complexity of OYA++ that we showed, and this is the complexity of OYAs. So the delta between the 2 complexities is really this additive red term that's due to preprocessing. In other words, like if you run the original OYA's algorithm, it doesn't start to converge right away. So it's like preprocesses itself, and until some point it starts to converge. So that's something that people also observe in practice. So we come up in this paper on a very nice idea to really remove this preprocessing from the total complexity. That is a technique we call undersampling. It works as follows. Recall that OYA's algorithm initializes itself with k random columns, and then it keeps multiplying the matrix on the left. Now for a moment, think for a thought experiment only that we initialize ourselves with only k/2 columns, and then we also run OYA's algorithm. We get an output that we denote by q prime. Now on this q prime, we can also demand that its correlation to z to be small. So this goal is by definition an easier to achieve goal than the goal above, because originally we wanted the k vectors to correlate with d minus k vectors by at most epsilon, but this time we only have k/2 vectors in this matrix q prime, and therefore this goal is, at least in definition, easier to achieve than the goal above. So what is really nice about this new goal is that we don't need preprocessing, so one can mathematically show that we only need this number of iterations before we converge to this goal. The underlying reason for this is really because of a very weird behavior of random matrix. Namely, that's about the so-called inverted Wishart distribution. Namely, like if you have a square matrix that is k by k, say each entry is like a standard Gaussian, then you can calculate that its singular values are not really uniformly distributed. So the smallest one and the largest one could be very far away from each other. But if all of a sudden you have over congestion, you have like a, say, 2k by k matrix, then one can show that the smallest and the largest eigenvalues are going to be at least up to a constant factor similar to each other. So it's really due to this like weird behavior of random matrix that we have to like shrink our initialization space to k/2 in order to, in other words, like if we shrink the original space to k/2, then we do not need preprocessing. The underlying mathematical reason is because of the random matrix theory. So we can show this. Now, motivated by this fact, we came up with the following algorithm that we call OYA++. That is, we initialize ourselves with k/2 random matrix as our random vectors. Then we run OYA's algorithm, we get some output. Now we append to this another k/4 random vectors to its right. We append to this output, and now we view these like 3/4 times k number of columns as a whole, and then we run OYA's algorithm again. We get some output. Now we append to the right of it some new like k/8 random columns. Then we view this as a whole again and run OYA's algorithm until at some point we get really k columns. Then we run OYA's algorithm and get some output qt. So this is our OYA++ algorithm, and it achieves goal number 1, for instance, with this number of iterations, total iterations. So this is a high-level description about OYA++. For practitioners listening to this talk, then I claim that in fact this also works in practice. So we tried it a little bit on our computers, and we realized that in this way of initializing the algorithm, not at once, but somehow like in this logarithmic fashion, like gradually, like we start to add the random vectors, then really like it helped in terms of the convergence of OYAs. So therefore, like we, even if you're not interested in the math, we hope that this gives some new insight about how practitioners can implement the OYA's algorithm in practice and run fast. So this is a high-level description about OYA's algorithm, about OYA++. In the remainder of the talk, I want to show you a little bit math about how we achieved, for instance, goal number 1 using OYA's algorithm. Not OYA++, just the vanilla OYA's algorithm. So remember that this is goal number 1, and therefore I am happy to assume that there is an eigengap between the kth and k plus first eigenvalues. And the goal that I want to achieve is to make this correlation to be small. Okay, let me now give you a high-level description about how we prove this. Let me introduce some notions. I'm going to call PT this matrix being the multiplication of everything until iteration t. And therefore, Qt, the final output, is nothing but PT times the random initialization, then right multiplied with an upper triangular k by k matrix. So this matrix R represents the Gram-Schmidt orthogonalization. Remember, we have Gram-Schmidt, and it can be described by this right multiplication to R, which is an upper triangular matrix. So this is the definition for P and for R. Also remember that Z is the matrix consisting of the last d minus k eigenvectors of the matrix, and V consists of the first k eigenvectors of the matrix. Okay, so these are the notations I want to introduce. So for a simple illustration, during this talk, you can feel free to think without loss of generality that all the eigenvectors are essentially the standard basis. Namely, like V contains the first k standard basis vectors, and Z contains the last d minus k standard basis vectors. So this is without loss of generality because you can always rotate the problem. Now comes our first technical contribution. That is, in the end, we have to analyze Qt, right? But Qt has this really bad behaving matrix R. It's bad because if I ask you like what is the second row, the third column of R, you don't really know what it is. It's defined through this complicated like Gram-Schmidt orthogonalization. And therefore, our first contribution is to get rid of R by the following reduction. Let us write Q as two pieces. So the first k rows of Q, I'm going to call it the red matrix, and the last d minus k rows of Q, I'm going to call it the blue matrix. And remember that we want to bound the Frobenius norm of the blue matrix, because that's our goal above. Now I claim that the Frobenius norm of the blue matrix is actually upper bounded by the Frobenius norm of the blue matrix, but right invert by the red matrix. So here's why. The red matrix has a spectral norm I claim at most 1, because the spectral norm of Qt is 1, so if you take a submatrix, it's not going to increase the spectral norm. And now if you invert a matrix by something whose spectral norm is at most 1, then this matrix in some sense gets scaled up. And indeed, this Frobenius norm should not decrease, but could only increase. So this can also be proven mathematically using some matrix inequalities. So I'm going to skip that. Now suppose you buy this. That is, the blue Frobenius norm of the blue matrix is upper bounded by blue, right invert by the red. Then I claim that we're in a very good shape, because if you expand out the definition of Qt, it's Pt times Q0 times R. That's the definition here. Now this R matrix shows up twice, not only in the blue one, also in the red one, and therefore it gets cancelled out. Now we have this very beautiful upper bound that sits on the right, which does not depend on R and only depends on Pt. And therefore, in order to bound the original Frobenius norm here, it suffices to upper bound this quantity at the bottom. Now let me define this quantity to be st squared, and we want to show that as t approaches to something large, then this quantity decreases below epsilon. So how do we show that? By induction, we know that pt is something defined from pt minus 1, then left multiplied with identity plus eta times xx transpose. And therefore, if you plug in this recursive definition and take expectation, you can quickly get some recursive upper bound on st like this. Namely, the expectation of st squared is upper bounded by a factor that's less than 1 times the same quantity of the previous iteration. So this is good, so it scales down this parameter, so that means st should decrease. But unfortunately, we also have an error term sitting here. Okay, so this error term depends on a different random variable, at, which is almost the same as st, except that you replace this z with like a different vector. You replace this matrix z with a vector x. So now, in order to analyze this error term, I claim that at least we cannot choose our learning rate to be too large. We have to choose our learning rate eta to be at most 1 over at. You can imagine that the smaller the learning rate is, then the slower the algorithm is going to converge, and therefore to get a good complexity result, we need to choose eta to be large, and therefore we need a good upper bound on at. But how do we bound at? There is a naive approach, that is to bound at as a function of st, which is possible, you can do it, but if you do it that way, you plug this inequality back into the definition of at, so you get a very nice recursive formula that's only about the S sequence. So this is good, you can solve the formula, but I claim that unfortunately you're going to get something that's slow, meaning that the final number of iterations is going to be proportional to d, the dimension. Kind of the underlying reason is because S0 at the very beginning is on the magnitude of root d, and therefore if you use this upper bound, your learning rate, at least in the first iteration, must be inversely proportional to, say, for instance, the square root of the dimension, and actually it has to be even inversely proportional to the dimension. So that's really too small, and therefore, like if you go through this analysis, the number of iterations is really going to scale proportional to the dimension. So that is bad. In fact, this is also the underlying reason that before our work, all the previous results except Jane et al., they really have this D dependency on the complexities. This is why they need this dependency. But we want to completely avoid this approach. So here's how we avoided it. First, we use random matrix theory to argue that A1 is actually good. So A1 can be upper bounded by something that does not depend on the dimension. It's only depending on square root of k. So that gives us hope, because at least in the first iteration, we can choose our learning rate eta to be not depending on the dimension. So something, say, 1 over root k. But how about the second iteration, the third iteration? We have to bound how this random variable at progresses as time t goes on. So in order to analyze that, we defined a random variable that's essentially the at, but this time we separate out the index t and the index s on this like matrix P. So we argue that this is also a random variable, and we can again use induction on S to show that it's also upper bounded. So this time we also have a very nice term so that it scales down by a factor that's less than 1, and also we have an error term that's similar to what we had above, but unfortunately we also have this additional third term that depends on a different random variable, bt. So bt is almost the same as at, except that you replace this xt with xt times the original matrix M. So now you see a pattern. That is, we wanted to bound S. To bound S, we have to bound A. We wanted to bound A, but then we have to bound B. Now, if you continue this process, if you want to bound B, you have to bound C, and so on. So at some point, we realized this is really a chain of logic. So therefore, let's just bound everything at once. So in the end, we defined the following random variable that takes into account all the parameters, the xt's, the ps, and some power of the matrix m to the ith power. Then we derived using induction that the expectation of c square is upper bounded by something that scales down times some additional term of a different I, and then plus some error term. So we derived something like this. Now the goal is to use maybe say martingale concentration to get a good convergence result on this quantity C. Unfortunately, this is not a martingale because those random variables also somehow depend on the future. Because like Ct in this definition depends on Xt, so it's something that depends on the future. So somehow like in the paper we discovered the decoupling technique that can somehow help us to condition on the future and then talk about the past. So once you do the decoupling, like you remove the future from the logic, then you have a martingale. So you can try to upper bound, you can bound the convergence of this martingale. But still, we run into some technical difficulty. For instance, even if like you have to compute like the variance of this random variable, you have to compute the absolute values. But even if you have computed all of them, I claim that we're still in some trouble because all those inequalities are assuming that the expectation of XX transpose equals to the original matrix M, which was sitting here. So while this were true at the iteration 1, but I claim that it stops being true as time goes on. The reason is because we have these error terms. And the error term is only bounded if, for instance, AT is small. We know that AT is small, maybe say with high probability, but that also means there's a failure event, meaning that if A is large, then the algorithm is going to fail. And therefore, we have to remove this failure probability from the entire space of probability events. And once you remove that, the expectation is no longer M, and therefore there's going to be like an additional error matrix sitting there. Now, how does the error propagate? You have to also analyze it appropriately and say it does not propagate too much. So in the end, we just showed that this works. Like there is a very careful way that we can bound the sequence of S, and therefore we get this result for OES algorithm. So that's from a very high level how we achieve this result. But also remember that this is not the best we showed. We showed that there's OER++ that does even better in terms of goal number 1 and 2, and we achieved goal number 3 here. So these are the high-level descriptions about our results in this paper. So something else I want to mention here, that is for those of you who are maybe only interested in the case of k equals to 1, I claim that we have a follow-up work that gives a one-page proof for this goal number 3 in the case of 1 SVD. So this turns out to be a sufficiently interesting subcase that has applications to deep learning. Okay, so that's a one-page proof, but in contrast, like our proofs to the right-hand side are like much more involved. So that's all I want to talk about in this talk. Thank you so much for your attention.